initially we start with the Kirchhoff's law again, and because that is going to be used for Wheatstone bridge, and there is simple in third, yeah, in third lecture in the combination of resistors. I already given to you guys what is a Wheatstone bridge, why it is used in general. Maximum number of times whenever we need to find the complex combination of resistors. There are multiple branches, there are different branches. Okay, sir, I got a camera issue. Okay, beta. Yeah, why not? Okay, so when we have this combination of complex and more number of resistors or instruments all together, then this Wheatstone bridge really help us. How so? Because of there is a functioning like using KVL. The mid branch is going to be currentless, or you can say there the resistance is going to be zero, because current there is no going, I mean at the mid branch the current is not going to pass using the KVL. So there is a one configuration which is going to help us really in finding the combination of complex resistance combination. Second, this particular kind of arrangement is used in the meter bridge. Meter bridge is kind of an instrument in which we have the resistance per unit length, or you can say resistivity per unit length per unit area, and we have either two resistance and we need to find the length at which that is going to be zero, and in vice versa. And in potential we find the voltage division rule, and why it is used, where it is used, and how the numerical problem going to be faced. Is this clear, everyone? Okay, so let's just start with, as we already discussed this thing, so I'm quickly revising you guys what it is in general. Kirchhoff's law, we have two laws. First law is based on the charge conservation. Second law is based on the energy conservation. Okay, so the first law is based on charge conservation. We already done this thing. Still I'm writing down conservation for the students who are not in the previous one, and that is based on energy conservation. Energy conservation. Okay. Just yeah. So the algebraic sum of all the currents found at each junction. Like what is a junction in the previous thing? This is 1, this is 2, this is 3, this is 4, this is 5th, this is 6th, this is 7th, this is 8th. So this particular point P junction. So here, if n number of 2 or 3 number is going to be coming inside current like this, suppose 3, 1, 2, 3, 4. So this is going to be out, and you can say the net summation of I equals to 1 to n summation I is 0. Means in this junction kind of thing, where all the current is going to be, some current is going to be inward, some current is going to be outward. So the net sum of all the current is going to be 0. And this is Kirchhoff's law, is based on the principle of conservation of charge, as we already discussed in the previous class. It is also called as Kirchhoff's law of current. Clearly, everyone, this is just a revision. We already done this thing. So if you want to know this in the great detail explanation, you can go back into the, you can watch the previous lecture video. Second law, in any closed circuit, okay, in any closed circuit, the algebraic sum, this is the main line, in any closed circuit, the algebraic sum of the product of current flowing in the different direction and their corresponding resistance, basically V. Why so? Because V equals to IR. V equals to IR. That is why it is also known as KVL, Kirchhoff's voltage law. Okay. Differences and the different electro-carrying EMF, electro-carrying forces applied in the circuit is 0. In mathematical language, IR, summation of IR, and that is the summation of EMF. EMF is nothing but the voltage of a battery of a cell when the current is not flowing. Okay, this is clear now, everyone? So based on this, like again for the example of in this way, suppose you have this resistance and this resistance, then this resistance, then this resistance, then this resistance, then somewhere between bulb also. Okay, now suppose we have one voltage here, now we have second voltage also here, we have third voltage also here. So meanwhile, in this particular kind of branch or combinations, suppose this is A, B, C, D, E, F. So here, the sum of all voltages, suppose we have EMF E1, E2, E3, and we have voltage V1, V2, V3. And okay, so in this way, this is summation of all voltages, Vi again, I equals to 1 to N, plus summation of I equals to 1 to N, EMF is going to be 0. Clear? So this is your second law of Kirchhoff's voltage law, or you can say Kirchhoff's second law, KVL, Kirchhoff's voltage law. This is also important. Why? So because in combination of this kind of instrumentation or this kind of resistance, we are going to find one by one, like for example for this loop first and for this loop, and then in this way the net current first, and more importantly the current or voltage at any particular individual resistance. Suppose R1 this is, R2 this is, R3 this is, this is your R5, and this is your R4. So the questions, how they ask question is specifically in complex manner, like find the voltage or resistance at this particular point. So how you can find? First of all, you need to find the net voltage using this KVL, and net current, and then current or voltage on individual resistance or instrument. They can ask on this because it is also have resistance of a bulb. So they can find the, they can ask the question like voltage of a bulb, what is going to be, or not resistance of a bulb in general, but resistance of a bulb is given, but current they can IB or VB. Is this clear? Okay, so we have two kind of you can say law. First is based on energy. First is based on charge conservation, and the second one is based on, this is your first law. First, that is your second law. Is based on this. So if you don't remember anything, at least remember this thing or understand this thing. Instead of remember, understand also. Okay. Is this clear, everyone, till now? Good. So this is somehow your arrangement of a Wheatstone bridge. I already given to you guys in the previous lecture, but still, like this is the you can say combination of 4 resistor only, in which this is your galvanometer, or you can say here we also a kind of instrument which is at which the current is going to be 0, even if we make this circuit complete or make this circuit complete also. Okay, so Wheatstone bridge, first of all understand this. Whatever I'm saying, whatever I'm telling to you guys, listen this. If you are not understanding anything, so let me know. So Wheatstone bridge is an arrangement of 4 resistors which can be used to measure one of them in terms of rest. Okay, means the resistance in terms of other. Here arms AB and BC are called ratio arms, AB and BC, and AC and BD are called conjugate arms. Okay, this is just the naming. We don't need to even think about this, but what is the main concept here? What is the main catch here? The Wheatstone bridge and the combination of resistance, where you can see something like this. So you can remove, or you can directly say that if the ratio of P by Q equals to R by S, this by this to the this by this, okay, or P by R, P by Q equals to R by S, then in the immediate effect, you can say the resistance or instrument which is in between these two resistance is going to be zero current, and that is going to be neglected or removed in finding the complex current. So in finding the complex, you can say branch or net resistance, combination of resistance. Clear? Okay. For example, this, if we have a PQ, I mean this ratio, or you can say whenever this particular condition is going to be fulfilled, for this condition, let me write it down. For this condition, when P by Q, the resistance, the ratio of resistance P by Q to the R by S is equal, the current at galvanometer, so you can say IG, the current at galvanometer is 0, Ig equals to 0, and when Ig equals to 0, so automatically you can say that and understand that when the current is going to be 0 here, this, so it means there is no resistance going to be. Is this clear? Okay, so this is your equilibrium state. The equilibrium state of a bridge, the ratio of the resistance of any two adjacent arms, these two adjacents are known as, any two adjacent arms is equal to the ratio of the remaining two adjacent. They can be P by R equals to Q by S also. But in general, P by Q equals to R by S. This is 1. So in this way, when we have the ratio is equal, for this condition, the current at galvanometer is 0, that is Ig equals to 0, means we did not need to consider the resistance of galvanometer, the resistance of mid branch or galvanometer, of mid branch or galvanometer. Okay, for example, simple thing you can understand from this. Suppose this is your one, or this is your circuit, because that the main thing we need to find here. Okay, and now what I'm going to do, just give me a minute. Yeah, suppose this is your one resistance, this is your another resistance, this is your another, this is your another, and this is this. This one. This is 2, this is 6, this is 4, or this is 12, and this is 10. So now you can see that automatically, without a doubt, and there is a current I. This is the condition of this A, B, C, D, or you can say E. Okay, F. So A, F, B, C, E, D, or A, B, C, D is now you can taken as a Wheatstone bridge. Clear? And you also observe here, like P by Q, 2 by 6, which is 1 by 3, and 4 by 12, which is also 1 by 3. Okay, here P by Q, if I put this P, if this is Q, this is R, this is S, so this is R by S, and that is 2 by 6 equals to 4 by 12, that is 1 by 3. So at this particular scenario, the current here is 0, whatsoever the current. So in finding you can say the total resistance, the net resistance, we did not need to consider this 10 ohm. What we are going to find, this 2 and 6 are in series, so R equivalent first, which is 2 plus 6 ohm, R equivalent 2, which is 4 and 12 ohm, and then both are in parallel, so 1 by R total equals to 1 by R equivalent to 1 plus 1 by R equivalent 2. This is the whole picture for which we are working hard enough, for which we are going to prove that also. Is this clear, everyone? Why we are doing this? Everyone? That is the catch. Just this particular thing we going to follow till meter bridge. Clear? Instead of simple resistance like this or instrument, in meter bridge we have a meter, 1 meter long, you can say wire, or we need to find the resistance of a wire at particular different. So if it is a meter length, so we have 100 centimeter length. So at any particular length, this particular condition, or you can say equilibrium condition, is going to be fulfilled. Or using this equilibrium condition only, we're going to find the resistance maybe, or maybe. Why should I use that particular word maybe? Because in this particular you can say analogy, they form the question. Either they give the length and two resistance, so they find the in the particular question we need to find the another length, or either we have two length L1 L2 and the resistance R1 R2. From the two resistance we have one resistance, the second resistance we need to find. Is this clear? But in every particular concept subtopic related to this Wheatstone bridge, either you going to use this particular equilibrium condition to find the net resistance of a complex circuit or a branch, or either you going to use this particular equivalent equilibrium state of a Wheatstone bridge in meter bridge. In both the way, this is the important thing, this particular simple ratio, or you can say very important. Is this clear, everyone? You don't need to worry how it is going to become. We're going to prove that also. With the help of KVL, we're going to prove this is going to be the case when we take this IG 0. How we prove this condition? We prove in a reverse way. Right now, what we are saying, if P by Q equals to R by S, then IG is 0. So if IG is 0, so this particular condition is going to be fulfilled also. So we are going to prove this equilibrium state in a reverse way. We're going to we're going to say IG is 0, and then we're going to prove this. Is this clear, everyone? Just type yes if it is clear. So, sir, what is the case when IG is not 0? Sir, when IG is not 0, so obviously this condition is not going to fulfill. Then we need to find this, you can say, then we need to consider this. Then we need to, that particular resistance in between is going to participate in the whole combination. Automatically, this PQ by equals to RS is going to fulfill automatically condition when IG is 0. If it is not 0, like it is a good question, if it is not 0, so then this condition is not going to fulfill. As simple as that. Clear, everyone? Because we are going to use this KVL, Kirchhoff's voltage law, and treating this, in that particular law, we are going to use this condition. If IG is 0, then only this condition is going to fulfill. Okay. So, yeah, this done. So, establishment of formula from Kirchhoff's law. So, automatically you can see that. So, according to Kirchhoff's law, in closed path A, B, D, A, like obviously you are not understanding what is going on here. So, let me take a snip of that and paste it on the next slide. Okay. I'm doing that a snip, so just give me a minute. or here we can paste. Wait. Okay, I can need to deselect this first. Is this clear? Or okay, it is going to hide something. So I want nothing. Now this is clear. Okay, this is equilibrium state. That is just written word. So now you can take it. Okay. So for example, using KVL, we are going to use KVL. So according to Kirchhoff's law, in a closed path A, B, D, A, A, B, D, A, we're going to take this. Okay. This loop and this another loop. So I1P plus IG into G minus I2R equals to 0. That is nothing but what we are doing. Suppose this is your I current. I current is going to be distributed in I1 and I2. So if I take this loop in this way, so I1 into 1, then IG into G, this is your voltage V1, voltage at Vg, and voltage at Vr. So instead of 1, I can write this is your Vp, this is your Vg, voltage at G, and this is your voltage at R. And the summation of all the three voltages is going to be 0. Clear everyone? First equation. Is this clear now everyone? Then in closed path BCDB, this BCDB. Now you can understand this. If it is I1 and that is I1 minus G, so then it is going to be I2 plus G. This is I2. Okay, this is I1 minus G. Not, it is not clearly written. Why so? Suppose there are, okay, how you can understand. Suppose here I1 is going to be 3 ampere and it is going to be 1 ampere. So that is 3 minus 1, which is 2 ampere. So in the same analogy, here we have I1 minus G. Okay, not this, I1 minus IG. Current I am talking about only, which is this. Here as well, I2 plus IG. Why so? This is not properly written. This is I2 plus IG. Why so? Because I2 is going to be in this way, IG is coming. So this is I2 plus IG correctly written down. So this is I2 plus IG, right? And then again, I minus I1G. Why so? Because I am taking this as a this. So if I am taking this in this loop way, so the current direction and my loop direction is going to be fulfilled in the same direction. But for this and for this, because current is flowing in this direction here and in this direction, D to C, opposite of the direction of loop direction. Again, D to B, opposite of the direction of loop direction. That is why opposite, negative, negative. Clear? So again, this is your potential at VQ, this is your potential at VS, and this is the potential of VG again. Because in both the loop, the galvanometer is going to be taken down. Clear everyone? Because if you understand these two only, then everything is done. If you have any question, query till now, so ask me here. Once this is done, everything is going to be remaining. Use this concept. Nothing more than that. Tell me if you have any question, query till now. Anyone? See, beta, please feel free to ask here. Then believe me, then you are going to be confused a lot. Because if this is the basic thing means this is the first step. If you are confused in the first step, so believe me, you are going to confuse in a meter bridge a lot. And in the following method or in the following steps also. Sir, why sign change in that VS part? Beta, sign change, see, in the previous class, I tell you two nodes of a KVL. Okay, here I can tell you. Even in the previous class, I tell you, what I'm saying. Yeah, I was telling you two nodes. First, in KVL, the voltage is going to be taken positive if it is going to rise from low to high, and it is taken as a negative if it is going to be taken, I mean, if the voltage is going to high to low, right? And the second thing, we need to take care of the sign of this particular, okay. We need to take care this also. Suppose if my current is going in this direction, right? And here in this direction. So the voltage here and the voltage here is going to be taken positive. Or not only voltage, the current in general. I1, I2. And here the current is going in this direction, because from this positive terminal, my current, net current is going in this way. So suppose this is I1 and this is I2. And this is I1 minus something, or you can say I1 minus I3. This is I3, and this current is going to be I1 minus I3 then. And obviously the circuit is need to be fulfilled, so this current is going to be I2 plus I3. So this plus cancel each out, and again here I have I1 plus I2. So when I take this as a loop, I mean, in my mind, I take the direction of a loop in this way. So automatically it is going to be negative. Is this clear, everyone? Because this is the main catch here. In which particular direction you are going to take your loop direction. If the current is going in the same direction, so the voltage at that particular branch, at that particular resistance is going to be taken as a positive. If it is in the opposite direction, so that we need to take a negative. So that is why you can see in both the loops I can take the same direction, clockwise, if I'm not wrong. Yeah, this is clockwise direction. Clear, everyone? So that is why here we take negative, or here only we take negative, because as you can see, for this particular loop A, B, B, A, here and here the direction of my loop, I mean this, and the direction of current is going to be same. But here the direction is going in this way and the current is going in this way. So that is why only I2R is taken negative. Here 2 times it is negative. Clear? Anyone? Any other question? Any other? Jyotsna, Parikshit, Hari Mahesh, Sai, Darshana, anything? Good. Okay. So then the values of resistors P, Q, R, S taken in such a way that no current flows through the galvanometer. Clear? So we are going to prove in a reverse way. So when the key K2 is pressed, suppose this K2 is pressed, this is the equilibrium state of the bridge. That is, in the equilibrium state, the deflection in the galvanometer is 0. Means we take here this condition to prove PQ, P by Q equals to R by S. As simple as that. So when we take this, suppose, I mean, we already make a connection, we turn on, we switch this K2 button, but the current is 0 here. So what's going to happen? When putting Ig equals to 0 in the above equation. What are the above equation? This equation 1, equation 2. You can write it down. Okay. To remember this. So when we put the Ig 0, so it becomes, okay, I can do that here. So I1 into P minus I2 into R equals to 0 at Ig 0. And here what we have, I1 minus Ig is going to be 0. So I1 into Q. I2, it is also become minus S 0. Okay. Is this clear, everyone? So now this is your equation number 3 and 4. And that is the same equation you can find on the next page. So I1P equals to I2R. What we have in the previous page, I1P minus I2R. This is my third equation. Okay, not this. Equals to 0. This is my third equation. And I1Q, I2S. I1Q minus I2S equals to 0. This is my fourth equation. So using third equation and fourth equation, we can get this. I1P equals to, I mean just, sorry. This is going to be shift here, nothing more than that. So it becomes positive. So I1P, wait, so this equation automatically we get from the equation 3 and 4. Or just divide I1 by I1. I mean now divide equation, or 3A, 3B you can write. So when you're going to divide, I1, I1 cancel, and I2, I2 cancel. So you automatically get this. So what we are doing here, first initially we say, if this is going to be the condition, so then Ig is going to be 0. So obviously we don't prove in a same method, we prove in a reverse method. What if I put Ig 0 deliberately? So when I put Ig 0 deliberately, automatically I get this relation. So that is how we proved. Okay. This is going to be very, very important, not only for your understanding part, not only for calculating the complex numerical problem, but this is going to be asked directly to prove this condition. First, how they can form the question on this. Okay, not here. Yeah. From here you need to start. I mean the question is going to be start from here, and I'll tell you the exact way in boards. You can say very, very important for both the things. And the question how they form. What is the principle of Wheatstone bridge? That is the principle of, I am going to write VB, not Wheatstone bridge completely. Prove its mathematical formula. Prove its mathematical formula. So this is your 5 marks question. First of all, you need to write this, the principle. Obviously, sometimes they ask what is a Wheatstone bridge also. So you need to add this slide also. But this is not going to ask. But if you are lucky enough. So you need to write all the 3 slides along with whatever I write it down. If you write it down, so they, I mean, understand better, like you know everything. Obviously, this is just for to make you more realistic what we are going to use. I mean, where we are going to use. This is your use. But at least you need to write till here. And then this page as a proof, and this diagram, and this equation, and then this page. Is this clear, everyone? So these 3 slides is automatically the long answer of your 5-mark question for boards. Is this clear, everyone? Okay, so this is the necessary condition for the balance of Wheatstone bridge. Generally, the arms with resistance P and Q are called ratio arm. The arm A and D with resistance R is called the known arm. Okay, what are they saying here? This is also important thing. Like if you are reading carefully, so you get to know. Generally, P and Q are called ratio arm. Means P and Q ratio are given to you. The arm AD with resistance R is known arm. What is the meaning of this? This particular resistance is known to you. And this CD resistance S is the unknown. They need to find this. I mean, they ask to find this. Okay, you are not getting anything. Obviously, I understand. Because without diagram, I am speaking since the last 2-3 minutes. So just wait a minute. Okay, so what is the meaning of this box? What it is? P or Q generally they ratio arm, like they given the ratio of P by Q. P by Q in the ratio 2 by 3. Obviously this is resistance. So suppose this is 2, this is 3. Good. And then AD arm is known. Means suppose you have the resistance of this which is 6 omega. 6 ohm. And then CD you need to find unknown. Okay. most in the cases, not every time. Is this clear, everyone? Is this clear, beta, everyone? This PQ is going to be given. Not good. Yeah, this is they given. Even this resistance R is something. They also. So what you need to find? S. How so? Just simple. Using this P by Q equals to R by S. They don't write directly this equilibrium balance condition, equilibrium condition, but they give you the condition like the current is zero, or here you did not get Ig always, some any particular resistance instrument, maybe bulb. Instead of this, how they can ask question like the entire thing is given and here you have a bulb, so the current at the bulb is zero, so find resistance S. Okay, so very simple. The ratio of resistance of a P and Q is 2 by 3. The resistance R is suppose 6 ohm, and instead of here Ig we have bulb, so the current at the bulb is 0. So in this condition, what is the resistance of S, or what is the resistance of branch CD? So automatically after reading this data, the moment you find the mid branch have a zero current, you can use this condition. Or sometimes they give you P by Q equals to R by S and find the current at bulb or any particular instrument which is in between. So automatically the current is going to be zero because that particular condition is fulfilled the Wheatstone balance condition. More importantly, Wheatstone equilibrium condition. Clear? I don't think so. I need to speak more about this after this. My throat is like enough on this particular chapter. I mean, on this particular subtopic. Is this clear, everyone? Now, or do you need any particular clearance or anything? Just type yes, everyone, if it is clear. So, no, sir, clear. Okay. I thought Yazina, right? No, sir, I need more clearance. Oh my goodness. Okay, good. So this is, I don't need to think like establishes from advantages. Okay, we can, this you can read it out. This is equilibrium state when P by Q equals to R by S, the total resistance. Okay, one thing importantly, how the total resistance you can find. Total resistance. I'm just going to write directly. R total is R1 into R2 divided by R1 plus R2, where R1 is P plus Q. Okay, and R2 equals to R plus S. So whatever written down, I just write down in a formula wise. This is automatically everything is written in this way. Okay, this is very simple. Like when at like balance Wheatstone condition, automatically the mid resistance is going to be neglected, and when it is going to be neglected, so P and Q are in series. Similarly, R and S are in series, and both are in parallel. So total resistance is this. Okay, because the resistor no, I'm not going to keep this even. So advantages of Wheatstone bridge. With the help of Wheatstone bridge, we can build a meter bridge. Okay, what we're going to find. The biggest advantage of Wheatstone bridge is to accurately measure the electrical resistance instead of using costly instrument. We can measure minute change in the bridge even in milliohm. I mean, these all are the you can say advantages of meter bridge. It is very easy to find out the unknown resistance as the rest of the three are easily known. We can measure strain and pressure using a Wheatstone bridge also. Strain and pressure, like how so? If you know the resistance, you can find the resistivity, length, area, and everything with the help of resistivity of a material and the resistance. So you can find the ratio of a length and area, which is nothing but force per unit area is strain. Change length upon length is strain, and force per unit area is pressure. So using this log Story relation. Is this clear, everyone? This is nothing, just a few advantages what you can read out even after the class. This is the result of, okay, we can focus here. The result of Wheatstone bridge can be easily affected by the temperature and EMF of a cell. As we know, the temperature, the resistance is going to be temperature related. Tell me what is the relation of a temperature and resistance? Anyone? Then I'm going to tell you. And the okay, I can read out. Meanwhile, you can write the relation. The Wheatstone bridge may also get affected if the galvanometer is not of good quality. It is easy condition. If it is not good quality, so the Ig is not going to be proper zero. Meaning of this is Ig is not zero completely. And when it is not completely zero, so we cannot use that particular balance condition. Completely. Okay. So this P by Q equals to R by S is not going to fulfill also. Just following this. Meanwhile, tell me the temperature and resistance relation. The Wheatstone bridge fails if it is not a balance condition. Obviously, there is no use to go through to know anything if it is not a balance condition. Again, this condition. Okay, important one. We can't measure large resistance with the help of Wheatstone bridge. One lag is if resistance are in the order of you can say 10 ohm, 50 ohm, so we can find that. But if it is in kilo ohm, so automatically in kilo ohm range, the resistance or the current in milli ohm is going to pass through this. So then this condition is not going to fulfill and we cannot use. Important one. The cost of maintaining the Wheatstone bridge is very high. You can visualize this. You can see, you can do the experiment also with the help of this Wheatstone bridge concept with the meter bridge in your first year of graduation or in your class 12th also. In good schools or maybe in mediocre schools nowadays also, we have meter bridge. If I'm not wrong, in my time, if my school can provide, so I think and believe and I hope your school also provide. Nothing, you have a pen kind of structure. You need to rotate a pen in this way on a meter, on a, you can say on a wire, on a simply meter 1 meter wire, and the point where the galvanometer current is going to be zero. So you can find just by changing the resistance of a connected wire, you can see the length of that particular point where the galvanometer shows you zero current is going to be changed. Simply, this is the experiment or the proof this particular Wheatstone bridge condition. Meanwhile, no one can give me till now the formula of resistance and temperature. How this is. After this class, you have a DRS. What is the meaning of DRS? Doubt removing session. And when I am asking something to you guys, the relation of simple resistance with temperature, no one is writing down here. What are you doing? See, you don't need to write. I don't know how many times I need to say. Whatever I write down here on this slide, on the page, you can get it automatically in the PDF form. And I hope and I believe my writing is that much efficiently good. So after converting it into the PDF form, you can able to write it down, or you can able to make your own notes. So when I'm asking something to you guys, why not you are providing me that? That is related to this. See, I am till now I did not explain this first point because you are not providing me the relation. So how can it be done? Tell me, beta. How it is going to be done? Tell me. If you are not know this, so we need to take care a lot. We means you and me both. Because in the coming weekly test, I am going to give you the whole chapter. I'm going to give you the whole chapter. See, still no one is replying. What is the resistance and temperature relation? Very easy. Very easy. Tell me, Yajira beta, what happened to you? The resistance and temperature. I think I given to you guys. Inversely proportional. Seriously? Seriously, are you serious enough? Yajira, I'm not expecting this to you at least. Resistance of a conductor. I'm saying true. Is directly proportional to temperature, and that is very easy relation. Guys, what are you doing? RT, resistance of at any temperature, is nothing but R rot 1 plus alpha del T, where alpha is the coefficient of temperature. Coefficient of temperature dependence of a material, different for different material. Okay, so what we are going to use this, I mean, what we're going to get from this relation, like the moment you increase temperature, so automatically the resistance is going to change, and we cannot fulfill the KVL condition, as simple as that. That's why I ask you this thing, and obviously, Kritika, you are right, beta. In general, what we can say, resistance of a conductor is directly proportional to temperature. This is proportionality sign, this is alpha. Maybe it look like same. Okay, I'll draw in a reverse key. Alpha, you can, this is alpha. And now you can make this alpha also. Is this clear, everyone? Beta, how this is going to help you guys if I ask some question to any particular chapter which already done. For example, capacitance. For example, electric field and charge. Very basic. This is very basic. So how you can going to see? That's why I'm saying don't try to learn. Try to understand, because everything is correlated. Clear? Is this clear, beta? You don't need to jump into the previous, you can say slide or notes or everything, anything. This is very simple case, and this is related to this simple analogy where I teach you what is the resistance. Obviously, if the temperature is increased, so ions or electrons more rigorously, more rigorously, what happened to me? Sorry, more rigorously they are moving. So when they are moving more rigorously, so obviously they oppose more amount of, you can say this flow of electron simply. Okay, so when they are opposed more in amount, so that the resistance is going to be increased, as simple as that. Because suppose someone is walking, so they are not going to collide with that much great speed or with that much great effect. But if 2, 3 or 4 persons are start running with great speed, then the collision is going to be very good, tremendous, at very good rate, or you can say at very tremendous rate. That is the simple catch. Is this clear, everyone, now? Is this clear, beta? Good. Okay. So let's do this quickly. This is your meter bridge. Nothing going to be changed. See, in Wheatstone bridge, what we have, P and Q, RS. Okay. So suppose this is a wire of length 100 meter. Wire of length 100 meter, not 100 meter, 100 centimeter, 1 meter. Wire of length 1 meter. So obviously we understand that resistance per unit length, or you can say resistivity. What it is? Resistance per unit length. Okay. So if you know the resistance, so the moment you need to find resistance, so that is nothing but resistivity into length. Or resistance is rho L by A. So suppose this is the wire of your unit area. Clear? So now from here we can remove. So now this is your resistivity. And suppose you know the material. So according to the material, you know the resistivity also. Anything. So now this resistance is directly dependent. Now this resistance is directly dependent on length. So what we are doing, we know this RNS. We move this jockey or this simple wire from here to here. The moment we get IG0, okay, at particular length L1, and then L2 becomes 100 minus L1, obviously because this is a wire of length 100 centimeter or 1 meter. So moment, or you can say the moment IG0, or you can say the moment galvanometer shows zero current. Zero current. Okay. The moment this current is going to be zero, we again fulfill the condition of what? This is the resistance of RL1. Clear? And this is the resistance of R100 minus L1. Or you can say RL2. Okay. Let me write RL2. Where RL2 is nothing but L2 is minus L1. Simply. So we again going to fulfill the condition of R by S, which is L1 minus 100 minus L1. R by S equals to L1 by L2, which is L1 upon 100 minus L1. Why so? Because at this particular moment, this is Wheatstone. Okay, let me write in the dot form. Wheatstone, balanced Wheatstone, balanced Wheatstone bridge condition. Clear? So that is we are going to see on the next page. Is it clear first of all what it is? And nothing new. We are going to use the condition of balanced Wheatstone bridge condition. Okay. If you want, so I can write here also. Using balanced Wheatstone bridge condition. Wheatstone bridge condition. Okay, everything now you understand. The moment Ig equals to 0, galvanometer shows 0 current. Again, balanced Wheatstone bridge condition we have R by S, L1 by L2. From why L1 by L2? From this. Okay, relation A. Okay, if you think like why should I directly put L1 by L2? So this is nothing but resistance of wire for length L1 for L2. So everything after that is theory. See, this is a catch again here, but this is question or this is your theory. Okay. So if you have any question till now, so you can ask me. If you don't, so read the theory or get a break, and then after the theory, this proof is already easy on the next slide. And after proof, we're going to do the questions. Is this clear, everyone? It is clear now, everyone? Okay. So you guys get a break also, read the theory because that is not going to anything new. I already tell you everything. Just it is in the written format. So there is a break of 5 to 10 minutes. I speak a lot already. Oh my goodness, 10 minutes break. Okay, read this, and after a break, we are going to prove, not going to prove, this is just a fulfill condition already. We already proved. So, and then after that, we are going to do the numericals. Okay, just see you guys after a 5 to 10 minutes. Hello, hello, hello. Am I audible? Hello, beta. Am I audible, visible clearly? Trivikram. Okay. So this is the same condition I already described in the previous slide, but still, for you guys, quick recap what it is in general. Just give me a break. See, four arms A, B, C, D. Okay, A, B, B, C, D, A, C, D, whose resistance are RS, RCM, L, and RCM, L 100 minus M, respectively. Okay, obviously from a Wheatstone base with AC battery arm and BD galvanometer arm, if the jockey is moved along the wire, there will come a point, equilibrium point, where the galvanometer will not show any current. Let the distance of the jockey at the equilibrium point be 1. Then the values of the four resistors of the bridge at equilibrium points are RS, RCM 1 and 100 RCM 100 minus 1, which is according to equation of Wheatstone bridge for the equilibrium condition. And again for equilibrium, sir, what is a jockey? Nice. Okay, jockey is something kind of a pan kind of structure. Okay, suppose a pan kind of structure in which the wire is attached in this side, and there you need to put on the wire and you need to slide. Okay, this arrow, beta, this arrow is nothing but a pan like structure, and on the using this pan like structure you need to touch single time and you need to slowly move, or you can say from one point to another point. The moment at which particular length, suppose this length is, you can say 20 meter for any particular wire. Again I'm saying meter, 20 centimeter. So at 20 centimeter, when you hold this kind of a pen or a joke is nothing but a you can say conductor, which is going to conduct this current whenever you touch here, and from here suppose, okay wait, whenever you touch here and from here to here you move, the moment your galvanometer and the galvanometer of this particular meter bridge is going to show the zero deflection, means zero current. Suppose the length is 20 centimeter. Okay. So obviously 100 minus L1, which is L2, is going to be 80 centimeter. Then it will be automatically 80 centimeter. So now we have the ratio L1 by L2. So maximum number of time they are asking the length, but sometimes they are giving the length, like how they form the question at equilibrium, I mean at the length of 30 centimeter of a meter bridge. The galvanometer is going to show you the zero current. Instead of writing that, simply they show you, they tell the at 100, at the length of 30 centimeter, the meter bridge shows the Wheatstone bridge equilibrium state or balanced Wheatstone bridge condition. So find the resistance S, unknown resistance S. R is automatically given to you. So R by S, L1 by L2. So automatically you can find S. Is this clear? Correction. Is this clear, beta? Good. Okay. So like this is R by C, RCM L1, RCM 100 minus L1. So RCM because as we know resistivity is going to be fine. So this RCM cancel each other, and that R by S is L1 upon 100 minus L1. So as soon as we find the value of L1, the unknown resistance R is obtained. This unknown resistance R is obtained in this formula, and that is very important formula, students. Why so? Because using this formula you're going to find so many numerical problems. Very, very important formula for meter bridge. Okay. Suppose this is a kind of jockey. The pen, the nib is instead of nib we have a little bit cut, and that we're going to move. Nothing more than that. Is this clear, everyone? Good. Do this question. This is very easy. Find the equivalent resistance between points A and C in the circuit in the figure below. And the exact same thing I already tell you, even I give a number, even the same number. So very easy question. Do that and tell me the answer. Then we have a still good amount of very it is, I mean what I'm saying, very easy it is. You just need to form this into the, I mean you just need to convert this into Wheatstone bridge balance condition, and believe me, this is balance condition. And then total resistance you need to find. I got 2.4 ohms, sir. Total resistance. Okay, let me check. No, better, not 2.4. How 2.4 is going to be correct? You need to find the total resistance, if I'm not wrong, right? Yeah. Between A and C. Okay. in questions like this, you need to focus on this also. Find the equivalent resistance between what? Between A and C. So this change in this particular kind of condition. So you are going to use Wheatstone balance condition also. Same A at this condition and C is going to be here somewhere. Okay. I'll tell you this one. I'm not going to tell the next one. See, adjusting this in this way, the equivalent circuit of the equivalent circuit of the given circuit is shown in below. So we need to find the net resistance between A and C. So automatically we make this particular tilt this, nothing more than that. So A, B, C. So now this 2 and 3 are in series and 4 and 6 are in series. Okay. Moreover, it is P, it is Q, it is R, it is S. And you automatically see that 2 by 3, 2 by 3. This is the balanced Wheatstone bridge condition. Got it? This is the circuit of a balanced Wheatstone bridge. Now, in the balance condition, this BD, okay, this BD is going to be 0. Why so? You don't need to even think the current here. The current here is going to be 0. And the current is here is going to be 0. In the balance resistance, VB equals to VD, so no current will flow through this. Now, equivalent resistance R prime, 5 omega. This R double prime, 4 plus 6, 10 omega. And this R single prime, R double prime are in parallel. So, you can use direct this R net instead of this. R prime into R double prime divided by R prime plus R double prime. And following this relation, 2 plus 1, okay, divided by 10 equals to 10, which is 10 by 3, which is 3.33. Directly you can find this R net using my formula, 5 into 10 divided by 15, which is 50 divided by 15. 15 3s are 45, 45, 45, 45, so and so. 15 3s are 45, point, again 50, again 3, again 3, and that is going to be recurrence relation. What is the meaning of recurrence? Non-terminating. Clear? You can use any particular method, but I tell you the shortest one. See, if you are going to follow this much whole written thing, believe me, you just waste your time in the writing section only. You don't need to write. Obviously, we provide you the full explanatory part, but the moment you rearrange this circuit into this, you don't need to write anything. You just need to write R prime. You need to write R double prime, not even write, calculate in your mind. And you need to use this formula and tell me the answer. And same analogy, same formula you're going to use, you're going to apply in any particular entrance examination. Is this clear, everyone? You don't need to write this thing. Obviously, if it is a subjective answer, then you need to write it down. If this particular question they ask in your board, but still they don't ask directly this. They ask along with what is a valence Wheatstone valence, what I'm saying, balance Wheatstone bridge condition, then they ask this. So you need to prove first, I mean not prove, but directly write it down like this: P by Q equals to R by S at Ig equals to 0, or when Ig is equals to 0, then following this everything. Is this clear? Better when I ask, I tell you this thing again, when I ask any particular question here, keep there in mind, make a alarm in your mind, make a note, I need to give answer ASAP within a minute. Believe me, here I am not giving you any particular question which is not going to be solved within 1.5 minutes, means 90 seconds. Believe me on this. And if I'm saying so, so the questions you are going to appear in JEE Mains examination a little bit complex. And I'm laughing on this, but since last 2 years the paper of physics is easy, so this time it might be the difficult one, it might be the complex one. So prepare on this note. Because what happens after each 2 year, the complex subject is going to be changed. Since last 2 year, since last year the chemistry, this year the chemistry paper is the toughest one, and the previous 2 years the mathematics, the mathematics subject have the toughest, or you can say complex examination, a complex question in JEE Mains. So now the number of is going to be physics. So if I'm saying so, you don't need to write this much theory. You just need to calculate in your head like this is going to be the Wheatstone balance condition, R prime 2 by 3. The moment you read this between A and C, automatically you can see this. This is in the series, this is in series, then only it is in, you can say, which particular condition? Wheatstone. Even if it is going to be in series, but it cannot be going to the series. Why so? Because current here is divide. So if you think like this is can be 2 by 4 equals to 3 by 6. Yes, it can be according to the ratio, but according to the simple analogy, because I need to find the current, resistance, net resistance between A and C. And automatically A and C, the current is divided. And again, the second concept, when the current is divided, so these resistance are in parallel. So they are not going to be in series. Then they are going to be in series. 2 by 3, 2 by 3. Got it? This. Because Parikshit solve in this manner. I know this. 2 by 4, then 3 by 6, 1 by 2, 1 by 2. So 2, 4, easily. 6 and 3, 6, 9. And 9 plus 6, 15. So 6 into 9. How much it is? 63, not 54. Okay, but this is not the right case. Why so? You can see that I1, I2. So they are going to be in parallel. Meaning of they are this one or this one. They are going to be in series. Is this clear, everyone? Is this clear, beta, everyone? Okay. So just whenever I ask any particular MCQ as a question like this in between the class, remember you are in JEE batch, not in the CBSE simple batch. You need to give me the answer ASAP. ASAP means as soon as possible. You don't need to write. Obviously, I am going to give you this so you can make your notes after the class, not in the class. That's why I solve here automatically. Even we have one page more. Okay. So now tell me this. Same condition you need to fulfill. But there is a catch here. Okay, I'll explain this. A resistance of 4 omega and a wire of length 5 meter. Okay. And a resistance of 5 omega are joined in series. Like 4 and 5 are joined in series. And connected to a cell of EMF 10 volt. Okay, where this 10 volt. Okay. And internal resistance 1 omega. A parallel combination of two identical cells. This is the story till now. This till now. Now we add two parallel EMF. This. Okay, a parallel combination of two identical cells. Identical cell means same EMF, same internal resistance is balanced across 300 centimeter. What is the meaning of this? Across 300 centimeter. That is going to be might be the wrong one. Instead of 300, we have 30. Wait a minute. Let me check this. R by L into 1 using E equivalent, which is E, which is this. 3 meter. Okay, yeah. 3. If it is the wire. Okay, yeah. Instead of 1 meter bridge, we have 3 meter bridge. So we can get this relation also. Across 300 centimeter of the wire, the EM of the each cell. So you need to find the EMF of this cell. Okay, a tricky question. Instead of 1 meter bridge, like in the previous slide, we understand meter bridge. Meter bridge. Okay. 1 meter only. Length I'm talking about. So instead of 1 meter bridge, we have 3 meter bridge, which is connected in series. Either you can understand in this way, okay, or either you can understand the meter, instead of meter bridge, we have 3 meter bridge. So now tell me the answer. Answer is you need to find the EMF of each cell, means EMF of any cell. Hmm. Tell me. Hmm. Try to solve this and tell me then. Uh, okay, did anyone get this solution or anything? Please let me know clearly at least. Uh, because now 1 minute for okay for potentiometer. Yeah, because that can be easily solved on the basis of potentiometer. Okay, if you know, so it's okay. If you getting more time, so we can switch this because that can be easily solved on the basis of this. What I am going to tell you, this formula. Okay, so I get this like here in the slide. The SME give me the answer directly. So if you're finding this, it's okay. If you don't, so we can switch on to the next question. We can come back to this after getting the yeah, after understanding the concept of potentiometer. If still you want to solve, I mean, I'm going to give you 1 minute because still after that we have 1 hour, so we can understand in a pretty much better explanation. Okay, what I'm saying, this question you can easily or more efficiently going to understand with the help of potentiometer. But if still anyone can solve this, so tell me. Okay. Okay, sure. I mean, I'm move out. What I move to the next question. We can solve this after understanding the potentiometer concept. This is page number 17. I remember. Okay. Because even if I tell you this answer, so explanation is going to be a little bit complex. Now this one is easy. Uh, Now in this particular question, what they ask instead of total resistance in the following figure, current through 4 omega. This one. Okay. So obviously, hmm, but how you can find the current? I don't give you this battery and so and so. Mhm. Okay, there is a catch in this. I don't know how many times I need to. Okay, see how you're going to find the current for this. One thing is missing here, the potential. Okay, just give me a minute. This one and this one and then this one and then this one. Okay, so this is your battery. So suppose this is of your 2 volt. So then the condition is going to be okay. So again, this is a Wheatstone bridge balance condition. You can see that 20 by 50, sorry, 20 by 4, which is 5, 50 by 5, which is 5 again. So this condition fulfills this I equals to 0, and then that is going to be easy one. Okay. So what this is, the answer is, since P by Q or Q by P equals to S by R, 4 by 20, 10 by 50, which is obviously 1 by 5 or 1 by 5, you can write it down in this way. So it is an example of balanced Wheatstone bridge condition. So no current will flow through 16 omega resistance. As we know that current divided in the inverse ratio, current through 4 omega resistance. What does it mean? As we know, if the current I1 is going in this way, so here beta we have I1 and here we have I2. Okay, so now either you can understand in this way, or either you can put the 2 volt and I1 I2 and then find the resistance at this. So the resistance at this is 1.4 into 20 plus 4. What is the meaning of 20 plus 4? This branch total resistance divide, this plus 50 into 10 divided by 50 into 10, R net. So using this is your resistance, total resistance. Okay, or how you can find in simple way. Following this is your 2 volt. So first of all find R net. So R net is easy, again R prime into R double prime divided by R prime plus R double prime, where R double prime is 50 plus 10, which is 60 ohm, and then R single prime is 20 plus 4, 24 ohm. So from here you can find the net resistance, right? Sorry, net resistance, automatically net current also. How you can find net current? Okay, I can give you on the next page. R net is this R single prime into R double prime divided by R single prime plus R double prime. Using this you can find I net, which is V upon R net, and then we need to find the current at 4. So current at 4, wait, I'll draw this on the next page also. You can understand what I'm doing. Just give me a minute. Okay. Yeah. So once you find this R net, whatever the, then I net is nothing. Focus here. V by R net, right? Because we have V now. Then I net is nothing but I1 plus I2. So the major thing is how you can find I1. But I1 and I2 is not going to distribute equally. Why so? Because the net resistance is here different. So to find I1, you need to find V1, because here and here the voltage is going to remain same because both are in parallel, right? So just give me a minute. So then what we're going to do, V1 equals to V2, where V1 is I1 into sorry, R single prime, and V2 equals to I2 R double prime. Okay. So if we get the ratio I1 by I2 using R double prime and R single prime, so we get the relation of I1 and I2. Suppose I1 becomes A times of I2, then use this relation, equation number A. So I total, suppose you get 4 ampere. I'm just giving you an example. So then A plus 1 of I1. Okay, using this and then using this B condition, you can get I1. A little complex thing, but this is the way. So just remove this. Why should I remove this? Because this is not you going to understand. Neither here in the question we provide you the resistance. Is this clear what I'm doing here? So from this relation analogy, beta, R net you find first, then I net is easily V divided by R net, and then follow this condition. Okay. We can remove this then, and then we can. This is just analogy. This is just example I'm going to do. Okay. Don't get like 4 ampere. You get the current. Is this clear, everyone? So now using condition, okay, I can give you, suppose I1 by I2, you get any constant A. So using I1, which is AI2, now using this equation B and this equation A. Okay, and from equation number 1, this is your I net. So now using equation 1AB, you can find I1 easily. I'm not going to explain much after this. Using equation 1A and B, we can get I1. Clear, everyone? Is this clear, beta, everyone? Okay. Everything I provide you, you just need to do a mathematics, nothing more than that. And if in any case you find a question like this, so obviously you need to do in this way. See, the what I'm saying, the condition, the resistance, what I'm saying, the current here is going to be same, I1 in both. Why so? Because both are in series, this one. Okay, and here we have I2. Why so? Because both are in series. Is this clear, everyone, or should I need to repeat this thing? Tell me, beta, everyone. Should I need to repeat this, or is it clear? I need to repeat, beta, Kritika. That's clear. Everyone, is this clear now? This is, I mean, I think now this is easy. Obviously not first, initially it is not easy, but now this is easy. You just need to follow this path and put the values, nothing more than that. Okay, so now I mean, this is application of potentiometer is first given, and then, because if after that there is no use, because this is the standard format of with the help of PPT teaching to make you real life correct. Why we understanding this? What is a potentiometer? We're going to explain. I mean, I'm going to explain. But in general, potentiometer is a device which is going to divide your voltage, and the use is audio control, transducer, television. Like transducer is nothing but it is a device which is going to convert your electrical energy into another form of energy. For example, loudspeaker, thermometers, pressure sensor, antenna, and so and so. So transducer, it is a device, it is an instrument. Okay, okay, let me write it down, which is going to convert, say in simple language, device, or instrument instrument which convert electrical energy into another energy. Electrical energy, electrical energy into another form of energy. Simple. It can be thermal, it can be mechanical, it can be sensor, it can be antenna and sensor. Like in audio control, the potentiometer is going to help you out. Like in household, we have 220 volt, but obviously our audio control or our PC or our phone is not going to handle that much. So this potentiometer is going to help there also. In television also, if we just provide this particular 220 volt or 240 volt, so then what happens? It is going to burn because that is high amount of voltage. So this potentiometer is going to help us out in dividing the voltage as simple as that. Clear everyone? Is this clear beta everyone? Good. So first of all, what is a potentiometer? Okay. So potentiometer is an electronics device that measures the EMF of a cell as well as the cell's internal resistance. It is also used to compare the EMFs of various cells. In most applications, it may also be used as a variable resistor. So this is a device which is going to give you the EMF of a cells with the resistance, internal resistance, or you can say variable resistor also. Like whenever we need any particular, in many applications we need variable resistors. So there also we can use this potentiometer. These potentiometers are widely employed in the production of electronics equipment that allows users to enter electrical circuits to achieve the desired output. For example, if I need to make any particular device or instrument which is going to burn or which is going to convert your electrical energy into this thermal energy or heat energy. So there I can use transducer or there I can use potentiometer. I can alter the voltage according to my wish, according to my will with the help of this potentiometer. And the moment I can change my voltage, so using this electrical energy or heat energy relation, which is VIT or VIT, or you can say V square RT, right? So now according to my, because I can change this, I can handle this, okay, I can alter this. So when I can alter this V using the potentiometer, using voltage divide method, I can alter or change the heat also along with time and resistance. Suppose I put resistance 1 ohm and I fix time also. So now my heat energy is directly proportional to V square, which I can alter with the help of this device. Is this clear? This is just a simple explanation or a real life analogy or example with which we are going to use in electrical iron, in electrical rod or heaters. Is this clear everyone? Obviously in electrical heater we are going to use the resistance, tungsten material, but in electrical iron we are going to use this concept also. Is this clear? Like you can see in electrical iron in the in now modern days electrical iron, you can say the plastic one, we have a knob. Like the knob is going to tell you where you need to put that particular knob to iron your woolen clothes, to iron your linen clothes, to iron your summer clothes. What that particular knob is doing, that knob is changing the potential, that knob is altering the potential according to your wish, and then according to that particular potential difference, your heat is going to be altered and you are going to iron your clothes according to that particular type of a flow. Is this clear? Everyone, is this clear? Right? So that is how we can use this thing. Moving ahead, potentiometer pin out. Pin 1 fixed end. This fixed end connect to the one of the resistive paths end. Pin 2 variable end. This changeable end can be connected to the wiper to give variable voltage, and this 3 fixed end, the second fixed end can be connected to the resistive paths other finish. Means in this 1, 2 or 3, this pin, okay, this second pin is going to alter your voltage with this changing path, or you can say wiper resistance, and the moment your voltage is going to be changed, the heat energy, the sensation energy, the mechanical energy is going to be changed. For example, you have in electrical fan we have remote or controller. Like at fifth you're going to run your this fan 4, 3, 2, 1. 1 is very slow, 2 is a little bit high, 3 more, 4 and 4. So this wiper is going to, suppose at 1 here, very low voltage, at 2 here, a little bit more, at 3 here, a little bit more, at 4 here, little bit more, 5th here, very high voltage. So the moment you put your knob of controller of, or you can say that particular electric fan controller here, the voltage is high, and the moment the voltage is high, electrical energy is going to be more, and the more electrical energy is going to be converted into mechanical energy, and your fan is going to run with great speed. And in reverse way, when you're going to turn this way, so again from 5th to 4th, 4th to 3, 3 to 2, and 2 to 1. Is this clear, beta? What is going on here? What I am explaining you? I am trying to explain you the concept, the science behind your fan controller or electric iron middle controller. That is the thing. Nothing more than that. Clear? Okay, this is not going to be asked in JEE, neither in boards, but for better understanding, you need to understand. Now, necessity for the selection of potentiometers. Potentiometer comes in a variety of shape and size, and their selection is based on the specific requirements, such as the one listed below. The structural requirement, resistance to change characteristics, choose a potentiometer based on the needs of the application, and choose the setting based on the circuit's requirement. This is just the requirement and necessity to select particular potentiometer for particular function for particular application. Nothing more than that. This is your construction. Like this is your variable resistance RH. This is your known voltage, and this is your known EMF. And just changing this resistance, we can change the voltage because V equals to IR. And if R is going to be changed, so this V is going to be changed. Is this clear? This is just a diagram or a construction. How are we going to change? What is this? We're going to see in next slide. Till now, is this clear, everyone? Everyone. Okay. So the fundamental, because even if you understand this, this is going to help you out. Nothing the previous slide. So the fundamental working standard of this depends on the way that the fall of the potential across any piece of the wire is straightforwardly relative to the length of the wire. Why so? As we know, simply you can understand with the help of this V equals to IR, Ohm's law, and we know that R equals to rho L by A. So the moment my length is going to change directly, in the same sense, my voltage is going to change. I'm not doing anything new. I'm just putting or reusing the formulas. We know that resistance is this. So if I put this formula, this formula in the above. Okay. Suppose this is your formula number 1, formula number 2. So I am just putting the resistance formula of formula number 2 into the formula number 1. So I get this. V equals, instead of V equals to IR, now my potential voltage is dependent on length or current, and that's what I want. Okay, so as rho and A are always constant and current I is keep constant by a rheostat. What is the meaning of this? This I is constant. What is rheostat? Rheostat is a changeable resistance. This RH. I is going to be constant with this. Okay. And for any particular wire, suppose you take any particular wire, for example, this particular wire. For example, this particular wire. So once you make this wire, so beta, the resistivity, because the material you choose already, right? So the resistivity and the area, because you make the radius, so this and this going to be constant. Is this clear? Because we already choose the material and this is material dependent. Material dependent, and this area is radius dependent. Area it depends on configuration. I can say that depends on configuration. Configuration is nothing but radius. We fix that initially. Clear? So that is how, using this rho and A are always constant and current I is kept at constant by this rheostat. So L rho by A is constant. Instead of L rho, this is I rho. This is not L. This is I rho by A become a constant, which is known as your potentiometer constant. So with the help of this, what we can see, this particular potential difference directly proportional to K, which is a constant, I rho by A. Rho is your resistivity, I is current, A is area. And with the help of this, my potential difference, difference of this particular potentiometer or voltage is directly proportional to L, which is V equals to K. Assume that a cell of EMF E with a lower EMF than the driver cell is added to the circuit. Now what we can say, let's say EMF E, the potentiometer has now become E in the potentiometer wire, say at any particular length X. Means simply we add one more cell. Okay, let me write down. We add one more cell of EMF E. Okay, and then this particular EMF, how we can find this particular EMF? I rho upon A into X. At this particular length X. X will given in the questions. Okay. So this is not L, this is I. So then automatically using the above formula, using the V equals to IR, that is nothing new I am doing. Again, V equals to I small r. Here V is EMF E and small r is rho X by A, because the wire is same, and for internal resistance we have internal length X. Clear? So again using the same condition, I rho by A becomes constant. So EMF of a cell is Kx. The same way we have potential, which is Kl. Is this clear till now? Tell me, this is very crucial thing or important also. This is clear or not? If it is not, so you can tell me. Can you repeat? Okay. See, I am doing nothing new here, beta, but just following the laws. What I am saying, using for the working principle of potentiometer, my main aim is to correlate my potential with this length, because this is the length. Suppose this is now length 1, this is length 2, this is length 3, this is length 4, this is length 5. So my main aim to relate the potential difference of the potentiometer using the potentiometer with the length L. Clear? Now to get this A, what I do, this is your diagram, and I need to find the EMF with this X and voltage, unknown voltage with this L. So what can I do? I need to establish a relationship between V and L and between E and X. So to do that, what I am doing, using Ohm's law, which is V equals to IR, then I am using the formula of resistance, which I know already, R equals to rho L by A. Rho is resistivity of a material, L is length, A is area. We know that whenever we make a wire, any particular wire, so initially we fix two things. We pick any particular material. Suppose I pick aluminium. So aluminium have some constant resistivity that is not going to change until unless I'm not going to increase the temperature. I'm not increasing temperature here. Area is going to be constant also. Why so? Because the more I can make wire, okay. I don't know why they call me in between. Okay, so the moment I can make this particular wire, so A is going to be constant, and I can make A constant with the help of this rheostat. Wait a minute, better give me a second, right? Just stick to this point. Just 1 minute. There is an important call I need to talk to that person. Hello, hello. Yeah, are you there? So what I am saying, with the following relation, the moment I make this particular, I mean, I pick any particular material, so the resistivity of a material is going to be constant. And the moment I make a wire, so obviously I need to fix the radius of a wire, so the area is going to be constant. And I, this, I means current, I is going to be constant with the help of this rheostat. Means rheostat is a device, even if I change my this variable resistance, but I going to be constant. I here is current. Okay, beta. So then this relation I rho by A, V, which is I rho by A L, and this is your constant thing. This I can put this thing as a K in the next slide. So V equals to KL, and then I use the same analogy for cell also. So V equals to KL, you can write it down this equation 1. E equals to Kx, you can write it down this equation 2. I can choose another color to make it more visible. This is okay. This is clear till now, everyone. I am just finding or correlating my potential with the length L and my EMF with the length X. Nothing more than that I'm doing. Okay. So now I need to find the EMF of two cells. So the EMF of two cells may be compared by using the by assuming that the first cell of EMF is E1, has a null point at length L1, and the second EMF E2 has a null point E2, L2 suppose. This is what, okay, just give me a, I need to give this diagram here. Just a minute, beta, just a minute. Because then you're going to understand easily. Hmm. Okay, just a minute. Hmm. Now what we are saying, suppose we have another cell also. Okay, suppose we have another cell also. this is E2. Now what I'm saying, null point is where the current is 0, and when the current is 0, again we get this Wheatstone balance condition. So the second EMF, now suppose the EMF of two cells, we need to find the EMF, or we need to compare the EMF of two cells. Our cell has EMF E1, this is your EMF E1. Okay, this is your EMF E2. This has length L1, and suppose this have length somewhere L2. This one. So at that null point is again where this particular I or this particular unknown voltage is going to be 0. So we have again this Wheatstone balance condition, and this is your relation. E1 by E2 equals to L1 by L2, and that is again very, very, very important relation. See, just understand this EMF, or you can say voltage, is directly proportional to length, or this is directly proportional to X, where, just a minute, where this proportionality constant are nothing, where this proportionality constant you can write KL, and this K is nothing, I rho by A. That is the whole story, nothing more than that. Okay, that is the whole story. We have nothing more than that. Is this clear, everyone? So this is going to be very helpful whenever you have the EMF of one cell and you need to find the EMF of another cell, or maybe you need to compare the EMF of two cells by giving the length L1 and L2. Is this clear to each and everyone other than Yajira also? Parikshit, Shrutika, Sudarshan, Syed, or Sai, Sada Murugan, Kayla, Netra, Kritika, everyone. Clear? Good. So this particular relation is going to help you out. And how the derivation is? See, I'm not saying that is going to be very important for boards, because for boards that is going to be omitted, eliminated. Only Wheatstone bridge you have. So even if you try to write every particular single step, that is not going to help you out. This is really important, this relation. Okay, wait a minute. This relation, but the understanding is okay. Okay, now construction of a potentiometer, types of potentiometer. There are different types: rotatory potentiometer, linear potentiometer. Like rotatory potentiometer is, you I given already this example, rotatory potentiometer in controlling the speed of a fan, controlling the heat or heat energy of a iron. Linear potentiometer, mechanical potentiometer, digital potentiometer. Digital potentiometer you can find in any particular lab, wherever the counting is going on, wherever the sensation is going on. Like in any particular entrance, like metro entrance or anywhere where the count is going to be necessary, like how many people is get inside the metro station or get inside the airport, right? There is a digital potentiometer. In airport, whosoever travels flight till now, or if no, so whenever there is a QR, like QR code is going to be you attach, or that is going to give your detail or data, like that is the flight, that is the rail, and that is at which particular time is it is going to be, at which particular platform it is going to be. That is used by digital potentiometer. Okay, so very big things we are discussing right now according to real life connection. Moving ahead, advantages of, I'm just going to quickly tell you. There is no possibility of getting mistakes since it is utilized the zero reflection strategy. The normalization should be possible by utilizing an ordinary cell straightforwardly. It is utilized to quantify. What I am saying already, it is written over here. Quantify means whenever the number of people, the number of person is need to quantify, it is going to quantify little EMFs because of exceptionally touchy. Exceptionally touchy means the moment you touch your metro card, you touch your any particular gate entrance, that is going to count, like one count, 0101. Okay, in view of precise, the potentiometer length can be expanded to get precision. Like the more the length, the more it is going to give you precision. Precision is more clarity, more close to the real number. At the point when the potentiometer is utilized in the circuit for estimation, then it does not draw any current. Means whenever we have any particular estimation, so it does not draw any current. Current is going to be constant. So automatically you just get the voltage on dependent on length, and whatever the function you need to do with this. It is utilized to quantify the inward obstruction of a cell, just as things about the EMF of two cells. However, by utilizing a voltmeter, it is unimaginable. Okay, disadvantages. The potentiometer use, I mean, you can read this all. I'm not going to read one by one. Okay, if anything is still not understanding to you guys, let me know in the next class. This is the main thing. Question. The resistivity of a potentiometer wire is this. The area of cross section of a wire is this. Find the potential gradient. Now, better potential gradient is V by L, if I'm not wrong. A, you can find potential gradient is V by L. I am correct. So everything is given to you guys. You just need to find potentiometer gradient. So potentio. I hope you understand why I am hurrying this everything, because I need to give you potentiometer gradient. This class assessment also. Stay there. Don't leave the class. And if you leave, so you are going to lose. I'm not. But still I'm saying don't leave the class. Just stay there for a 10 minutes extra. Okay. So we have V, we have L. Put the value of V with the help of IR and everything, then we have substituting the value. So that is your potentiometer gradient. Is this clear, everyone? Tell me, beta, is this clear? Okay. Okay, this is the summary. But before summary, I need to write this one thing. As I'm going to write each after each class. Do the homework also related to this class, because that is important. This class, very important. Okay. Moreover, let's come back to the page number or slide number 17 once for you guys. I mean, I can teach you without that also. Yeah. So this question can be easily solved with the help of potentiometer knowledge. Now, how so, why so? We need to find the length of a potentiometer, right? I mean, we need to find the EMF of a cell, and the EMF of both the cells are equal. Why so? Because cells are identical. EMF of a cell. We need to find this. We have everything, like we have resistance this, 5 omega resistance of this, and 1 omega this. So in total, this is everything is in series, 4 plus 1 plus 5, 10 omega resistance. Okay, let me explain to you guys on the next page. What is the meaning of this? The correct option is B, first of all, and this is your answer. Wait. This is the proper explanation. So correct option is B. B here is 3 volt, 3.0 volt. That is correct answer. So how? In the potentiometer circuit, net resistance is R1, 5 plus 4 plus 1, 10 omega. And any provide E1 is 10 volt. As you can see, this is your 10 voltage, right? Then equivalent of any cells in parallel, E prime equals to E, because there is no internal resistance given here. As you can see, there is no internal resistance for this E1 and E2, which are in parallel. So obviously when they are in parallel, so EMF is going to be equal also. Now, and resistance 5 by 5 into 3. What is the meaning of this? Due to 3 meter balance length, as we have the resistance of this whole 3 meter length is, I mean whole this 5 meter length is 5 omega. So the 3 meter have 3 omega, because you can understand resistance per unit length is 1 omega, because 5 meter length have 5 omega resistance. So 1 meter length have 1 omega. So then 3 meter have 3 omega. As simple as that. Unitary method. If you are confusing what it is unitary method. Means if you can buy 20 pencils for 40 rupees. So how much is the cost for 5 pencil or 2 pencils? Unitary method it is known. Okay. Then at balance condition, at balance length, both the circuit have equal currents. Then I1, I equals to E by R1 equals to E2 by R2, which is 10 by 10, E by 3, because this is 10, E1 is the potential 10, resistance is 10, E we need to find, and 3 we already have the resistance of the null point, and this is how you can find the voltage. Is this clear, everyone? Is this clear, beta? How you can find easily this 3 volt with the help of this thing? Okay. Okay, good.